So we are going to cover physics and biology of audition. We're going to roll that right into the perception of sound. This is okay. Most of you are not going to pick up that there's a difference in the two of these things. So you're fine. You're good to go there, so no worries. And Madison, it's just going to be a thrilling day all around.
Can't wait.
That's what I thought. Okay, so Chapter 4, Chapter 5, then we're going to spend the last probably 4 hours of class, Marissa, doing the lab activity. And it is a brilliant lab activity that you are going to have so much fun. I mean, you thought last week was great when you got to stab people? This is even better. Because someone's going to be blindfolded. And then you have to guess who stabbed you. That's not true. That's not true. I mean, that's not true at all. All right, so we need to talk about the physics of sound. What's really important is for you to understand the nature of the stimulus so you can understand, Justin, the nature of the receptor and why things are structured that way and why that particular sensory system processes information in a particular way, right? And so I think the first step we need to do is we need to think about what is sound. Sound, it's these pressure waves, okay? And it's carried by these vibrating air molecules traveling at approximately 335 meters per second. Are any of you athletes? Has anybody ever tried to run 335 meters per second? You ever tried to run like 335 meters in like 10 minutes? Because that's, sort of multiplied by 3, roughly, it'll tell you how many feet that is, right? So that's about 300 yards or so, which is that's down and back a time or two on a football field, right? In a second, it does this. I am required by the contract that I signed to mention at this point one of our sort of local folks, right? This is a state law, and then Marshall adds like an extra layer to it. I'm required to say Chuck Yeager at this point in the lecture. Why am I required to say Chuck Yeager at this point? Anybody know? Yeah, sort of the first dude to break the sound barrier, right? Which is kind of a big deal, right? It's kind of a big deal. He did this in his spaceship, not really a spaceship, sort of a spaceship. I've been traveling that fast at that time. It was the Bell X-1, right? The aircraft that he used to break Mach 1. So you'll need to know that. Because when you graduate, and I assume you all want to do that, right? And you're going to walk across the stage and you're going to like shake hands with the dean of your college and the president's going to be there. He's going to ask you some fact about Chuck Yeager. And if you don't know it, they'll put you off the stage. I saw it happen. That's a true story. I've got a Chuck Yeager autograph at home. That is a true story, actually. How many of you are Yeager scholars? How many of you know a Yeager scholar? Do you know one? Pretentious, aren't they? I'm just kidding. That's named after Chuck Yeager, right? So you're kind of following the theme here, right? So we've got compressions. That's the parts. This is really, I know, Abby, hold on. The compressions are the parts where, parts of the wave where the air molecules are closer together and the pressure is higher, right? And then we have the refractions. That's where the air molecules are farther apart, so the pressure is going to be decreased. Okay. This is your basic sound wave, or basic wave of any kind, right? We're going to kind of cut this guy in half. Keep in mind this is really sort of a three-dimensional rippling structure, right? We're not going to really think about that at the moment, okay? We have sort of a 0 point, right? That's in the middle. Here's a compression, that's an increase in pressure. A rarefaction, that's a decrease in pressure. Not a big deal. Peak to peak, or you can measure trough to trough, either one, it's totally up to you. Or you could measure any arbitrary point in between to that exact same arbitrary point. On following wave, that's going to be one cycle, right? And so peak to peak is typically the easiest because you can measure these peaks, right? And then they're clearly delineated. So you've got peak to peak, that's going to be one cycle. The amplitude is going to be sort of from the midpoint up to the peak. You could also measure that in the opposite direction from that midpoint down to the trough, okay? This is a sine wave. We are going to talk a lot about sine waves today. We're going to talk a lot about sine waves in the future. Okay. This is what a sine wave looks like. And this is a sine wave right here, up and down, up and down, up and down. Now this can be used to describe, in this case we're talking about air pressure. We can use it to describe, when we get to the vision chapter, it's going to be contrast, right? Or, luminance values, okay, so dark and light. There's sort of two important things we want to think about. We've already talked about amplitude. The other is going to be what we call period or frequency. They're kind of the inverse of each other, right? Frequency is going to be how many peaks are coming per second. Okay, we're going to measure this in hertz. That's cycles per second, right? So 1 hertz is 1 cycle per second. 10 hertz is 10 cycles per second, right? And that's going to be the frequency. And we'll talk a little bit about that in a moment. So, the simplest sine wave. It's got 3 things. Frequency, we just talked about that. That's the number of those compressions and refractions per second. Okay? Because this is going to be traveling. The whole thing is traveling. I know you're going to be confused. You're thinking like, well, isn't it all traveling at 335 meters per second? Yes, it is. Okay? But that could have only 1 peak, right? And how many peaks then are going to come by per second? Well, just that 1 peak, right? But if there are 10 peaks, right, then they're all moving at 335 meters per second, but they're all going to move by within 1 second, right? So you're going to have 10 peaks, so that's going to be frequency. We already talked about amplitude. We measure this in decibel, right, which is sound pressure level. This is a logarithmic scale. How many of you know about logarithmic scales? How many of you are earthquake aficionados? I don't know if those things exist, but we're going to make it right now. Who wants to be the earthquake aficionado for the class? Don't everybody get excited at once. You don't like get a hat or a ribbon or anything or an extra grade. So just calm down. The Richter scale is a logarithmic scale as well, right? pH is a logarithmic scale. How many of you know about pH? Yeah, there you go, right. Awesome. So, Macy, pH is logarithmic, right? So, 7.4 to a 7.5, that's a pretty big jump, really, right? 7 to an 8 is massive. Okay. So, decibels are going to be measured in the same way. Hey, anybody want to know why you capitalize the B? How many of you have a telephone? Monica, you really were sort of reluctant to answer. She's like, is he going to call me? Because I don't know if I want to raise my hand on this. You were really reluctant on it. So if you don't have a you may not call it a telephone, you call it a cellular telephone, right? If you really want to have the whole thing there. I'm assuming all of you have cell phones, right? Okay. So you remember before they had cellular phones? You don't. That's okay. Cellular phones have not always existed. Ask some really old person about it, right? Like your parents, okay? Because they're probably really old, 50, right? Is that roughly, most people's parents are probably 45 to 53. Is that probably a good estimate? For most folks, right, Madison?
Yeah,
that's probably,
for
the most part, right? I mean, some people are probably a little older. I'm trying to think, how old are my parents and subtract off some years to figure out how old I was. Right, whatever. So, you had those other things, right? They're connected to a wall and have wires. There was this guy, it was a long time ago. You do not know anyone who was alive when this happened, because this happened the 1800s. Alexander Graham Bell, anybody heard of that guy? And he's like, hey, you know what would be awesome? If I could get a pizza but not have to go to the pizza store, and I could just call them and they would bring me a pizza, because I'm certain that's why he invented the telephone. Right? Because it was not for any other purpose. So he invented the telephone. His last name was Bell. The decibel, sort of named after him, so that's why we capitalized the B. Okay? I know, right? It's just like this epiphany all of a sudden. That's why the B. And hertz. Why is hertz capitalized? because the Hertz car rental company paid a lot of money a long time ago. No. Again, it's named after a person, right? It's named after Hertz, and he was the guy who described frequency and these cycles per degree. So there we go. Okay, so we understand frequency, we understand amplitude. The other thing is phase. Now, phase is really hard to think about if you don't have a reference point. And a good reference point is another wave, right? So what is the phase of something that has no reference point? It doesn't really matter, right? It doesn't have a phase in one sense, right? So, but this is the part of the cycle, like, I know this is confusing, you have to think about it like at any given point in time, measured in 0 to 360 degrees. So if we want to think about phase, let's see. So here's sort of phase, right? So this is like 0 and there's like 90, whatever. If we were to shift this, then we would say those two waveforms are out of phase, right? So one has been shifted sort of forward or backward, you want to think about, you know, it doesn't really matter. But it's shifted, in this case it's shifted like 90 degrees, right? Okay, so we just shifted the whole waveform over. We didn't do anything else to the waveform. We didn't change the frequency, we didn't change the amplitude. We just changed when it started, right? I know everybody here is in a barbershop quartet, right? Okay. Marissa, what's the name of your barbershop quartet? I'm going to put you on the spot.
I don't have one.
You don't have one. Anybody have a barbershop triplet and they're looking for a fourth? Marissa, I would love to say right now what sort of range you sing, but I have no idea what they're called. So I know like soprano, but I don't know if that's a male or female voice, so I didn't want to throw that out. But then there's also like alto. I know baritone is not. That's not for you. But if anybody needs someone, Marissa's like. So, how many of you, not in the barbershop quartet, how many of you have ever, because this is so much fun, how many of you have ever done what they call singing in rounds? Yeah, right? So like row, row, row your boat, right? Anybody a fan of that? So that's a winner. So Imani, you like start singing row, 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 or whatever, right? And when you get to like gently downstream, then somebody else starts up with like row, row, row your boat, right? And so they're like really out of phase from you, right? But that's intentional because it's going to create, whatever reason they do this, it's going to create some nice sort of melodic something or other. And so you do this, right? So that's what we talk about with phase, right? So that's going to be something that's going to be out of phase, kind of like singing in rounds.
One thing I think is really cool about phase is like if you're recording a drum set for an album or something, you place a microphone on each individual drum, and you have to make all the mics equidistant from what you're recording, because since the arrival time would be slightly different, like once you'd hear the drums mixed down, you'd be like, this doesn't sound good, it sounds sloppy.
Yeah.
But it's because of the ever so slight arrival time difference.
Yeah. How many of you are Willie Nelson fans? How many of you are Willie Nelson fans and realized he actually sings like music? Because I think some people in your age group are Willie Nelson fans for a different reason, and that's fine too. You know. So I actually I can't remember who the female artist was, and she said singing with Willie Nelson was like that, like he's always out of phase, right? And so she said the best you can do is just not listen to him and just try to like sing, because he's always sort of like behind or somewhere else, right? And if you don't know Willie Nelson or have listened to a Willie Nelson song recently, at least for the purpose of this class, give it a try, Oliver. Don't convert to Willie Nelsonian. I don't know what you call those. Just made that up. You know, but at least so you understand the concept, right? And I think that's. But yeah, the drum sets, man. That's. So what do you do? You get like your micrometer out and.
Just measuring tape.
Yeah, that's cool.
Try to put each one about 40 inches from the snare.
Yeah, that's cool. There you go, right? How many of you have a drum set? How many of you ever had a drum set? You had one, Marissa?
Yeah. I played drums too when I was
Really?
in high school.
I used to play drums.
Did you?
Yeah, I did. I had this beautiful vintage, oh man, it was beautiful. It was from the 60s. It was a beautiful vintage pearl set. It was like a jazz set. It was beautiful. I sold it. And then the guy I sold it to was like my friend, and he sold it, but everybody made money off the deal. So we all made about $200 each time. So I don't know where it is now. I only paid like $300 for it. I looked them up on the internet the other day. It was like $1,200 to get one, like that exact version that I had. It was All right, so frequency, hertz, phase. We got a handle on this? That's awesome. So this is like super simple, right? And we were just talking about this one sort of like, isn't that a beautiful sine wave? I don't see you making a better one, Carrie. Don't even try it because you're not allowed to use the mouse. So a pure tone, what we call a pure tone, is simply one sine wave, right? One sine wave of a given amplitude, of a given frequency, and that's all you get. It's perfect and pure. Natural sounds, unfortunately, are a lot more complex than that. And they're actually treated as a large collection of simple sine waves added together. So you're going to have this sine wave, and then on top of that you've got another sine wave, and then you have another sine wave kind of riding on top of that. We're going to have these multiple sine waves together. Okay? There is a mathematical procedure. It doesn't require you to be anesthetized, but so it's outpatient work. You just go in, you get the procedure done, and you're finished. It's a mathematical procedure. It's called a Fourier analysis. Okay? Now, I'm not going to expect you to do a Fourier analysis. I want you to think about this process. Abigail, what was that? It was just, like it was. Justin, you heard it, right? I could see it from here. It was like this. You don't have to. You should learn. You don't have to answer those questions from now on. You should have just said no. That would have been better. You're like really sighing about this Fourier analysis. The basic idea here is to sort of pull out components of amplitude, phase, and frequency, and you can display these in a different format so that you can analyze them, right? So I'm going to show you this like funky sine wave, and you're not going to be able to really analyze a lot of that, but we can pull out the components, right? And then we can do this. Has anybody ever done a Fourier analysis on anything before? Or heard of a Fourier analysis?
I did.
Yeah, they're kind of cool, right? I mean, they're kind of fun to think about. You can actually just get like a computer program to do it, so you don't have to do it by hand.
That's what I did.
Yeah.
I had my guitar rig set up, and I was switching the order of the effect pedals and seeing how the order would affect what ends of the spectrum would get cut out, like the lows, the mids, and the highs.
That's pretty cool. You don't realize like how much goes into music, but it's really fascinating. Anybody else a musician other than Marissa? We've got Montana here, 2 drummers. Anybody else play? Natalie, you were like almost into that, right? But not really. That's fine. Don't offer any details. That's okay. Just keep it to yourself. We'll guess. We'll guess. Be fun, right? Whoa! Look at this. That's complicated. This top line is just a natural sound wave. This is actually from a clarinet. How many of you know what a clarinet is? Yeah, all right, very great. So the clarinet, right? It's kind of that instrument like this long. It's got a little bell at the bottom. It's a reeded instrument. You put air in one end, the noise comes out the other, right? That's how you can tell it from other instruments. No, most other instruments work the same way, right? So you have this clarinet, right? So you guys have all heard of clarinet probably. If you've not, imagine an instrument you have heard. Saxophone. How many of you have heard of saxophone? You can imagine the same thing. French horn. I don't know, it doesn't really matter. Okay? Now, so this is not a pure tone, right? Even though this is, I think this might be a C note. I don't really know. And it doesn't really matter. But it's one constant, continuous note. But notice how kind of wiggly all those lines are, right? What we can do here, Regan, is we can actually pull out each of the component sound or sine waves from that complex sound. And if you take a look at this, you can see here's a nice low frequency note, right? Low frequency sine wave. You can pull out of that note. Here are some higher frequency sine waves. Now notice something about these higher frequency sine waves. More peaks and troughs per second, right? This is actually only over 0.004 seconds, right? So more peaks and troughs, so higher frequency, more peaks and troughs per second, higher hertz. Higher frequency, we have lower amplitude in this case, right? So that's going to become an important concept in a moment. And the other thing to notice is the phase, right? So notice the phase. It's kind of hard with this large, low frequency sine wave, but when you look at a couple of these other sine waves that are lower amplitude but higher frequency, so this one in particular, notice where that peak is compared to the peak of this other sine wave, right? So their phase is shifted a little bit, okay? And obviously that's going to change as we go across. Notice the peaks and the troughs because they're different frequencies, but no real worry there. So, when we pull out these component sine waves, and this is us doing that Fourier analysis, right? There's some things that we want to keep in mind. This component with the lowest frequency is called the fundamental. Okay? This guy right here, that long, slow, low frequency, high amplitude component, that sine wave is known as the fundamental. It is this sine wave that gives the sort of characteristic pitch to that full complicated note coming out of the clarinet. Okay? So if you play, can anybody like hum like a C note? It's like, ah, I don't know.
Should have brought the tuning fork.
Should have brought the tuning fork. Yeah, so we've got a tuning fork. That would have been fun. So, you have a frequency. If you pull out that fundamental frequency from that full complicated sound, it's going to sound different, okay? Because we don't have those other, here's a sort of preview, they're called harmonics. We don't have those other harmonics, right, to add to the timbre of the note, what we call that. But what we do have is sort of that same sound, right, that same pitch, the same tone, okay? So, how many of you are now familiar with clarinets? And let's think about another instrument. We've talked about the saxophone, for example, right? Can you play a C on a saxophone? Yeah. Can you play a C on a clarinet? Okay. Can you play them both at 100 decibels? Sure. So you can play the same note, and you can play this at the same amplitude, right? So our frequency is going to be the same, roughly, right? But they're going to sound different, right? How many of you know that a clarinet and a saxophone sound different? If they didn't, we would only need one of those instruments. You wouldn't need both, right? You would just have people who play the clarinet or people who play the saxophone. You wouldn't have groups in both categories if they sound the same. The reason they sound different is that timbre, right? Is the harmonics. That harmonic signature is going to be different, right? Going from a saxophone to a clarinet. The fundamental is going to be the same, Regan, because it's still a C. It's still got to be that same fundamental frequency because that's the main characteristic. But those harmonics that ride on top of that fundamental, those are going to be different as we move from instrument to instrument. Okay? Questions about that? See, Abigail, it wasn't that bad, right? But we're not finished. So hang in there. And we're going to be really fun now. Okay, so now, who loves graphs? Who thinks they're going to need to be able to read graphs to pass this class? Yeah, some more hands should go up, right? Who thinks they're going to have to create a graph to pass this class? You've already had to create a graph, right? Okay. So get ready for more. All right. Now, this is sort of cool. So we can plot like frequency versus amplitude, or frequency versus, in this case, phase. Okay? Now, we're not going to talk as much about the frequency versus phase, but we can figure things out. What do we know about the fundamental frequency? That fundamental component. Abby, we know two things. And those two things are on this slide. Right? One of those is it is the lowest frequency, and the other is it is the highest amplitude, right? So we know those two, and we can measure both of those, right? Because we can do this Fourier analysis, we can pull out the component sine waves, and we can find the one that has the lowest frequency. And every time we do that, it will have the highest amplitude. Or we can find the one with the highest amplitude, and guess what? It's going to have the lowest frequency, because that's the fundamental. And so if we plot that, right? So we've got our sort of normal XY plot. We have frequency on one axis, and we have amplitude on the other. This is frequency from 0 to 4,000 hertz. Again, 1 hertz is 1 cycle per second. 4,000 hertz is how many cycles per second? It's right there in the hertz. It's 4,000, right? So that's easy. Now, this dot right here, anybody know what that dot represents? Look at that great arrow I'm drawing. All right, let's think, what do we know about this, Abby? This is on the amplitude scale. Do you see anything above it? So guess what? It has the highest amplitude. Wow, that probably means something, right? Now, this scale, this is the frequency scale. Is there anything lower than that frequency represented by dots on this graph, on this chart? No. So it has the highest amplitude and the lowest frequency. So that makes it the fundamental right there, right? These other dots are the harmonics. Okay? So we've got the fundamental, and everything else is a harmonic. Now here's the awesome thing about harmonics. Okay? Harmonics are always going to be whole number multiples of the fundamental frequency. Okay. So how many of you can do math? You should all make Abigail do it because of the size she gave earlier. This is easy math. This is multiplication. So you can multiply, you know your fives, right? Because you had to learn this in like the 5th grade, like 5, 10, 15, right? Okay. If the fundamental frequency is 5 hertz, if the fundamental frequency is 5 hertz, what are the possibilities? Now, not all of the harmonics are going to be present, but what are the possibilities for the harmonics? They all have to be whole number multiples of 5. Absolutely right. So, what's a good harmonic for a 5 hertz fundamental? 20. Is 20 a multiple of 5? Give you guys a moment if you need to get out paper and do long division. It is. Okay. What about 22? No, that doesn't work, right? So 22 hertz is not going to be, if you have a component that's 22 hertz, guess what? Your fundamental is not 5. Your fundamental is something else, right? All of your harmonics will be whole number multiples of that fundamental. That's pretty exciting, right? Anybody else excited about? So what if it wasn't 5? What about 7? Who could multiply by 7? Because I want to make sure you know it doesn't always have to be 5. So if it's 7, Oliver, is 21 a possible harmonic? Yeah, because 7 times 3, right, is 21. But what about 15? No, you can't divide 7 into 15 an even number of times, right? What if your harmonic, or what if your fundamental is 3.5? Because it could be 3.5 hertz, right? Is 7 hertz then a possibility? Yeah, 7's 10.5, that's a possibility, right? Okay, so all of these are then possibilities. It doesn't have to, the fundamental doesn't have to be a whole number. That's what I'm going to let you know. Okay? But the multiples have to be whole number multiples. So a harmonic cannot be 1.5 times. Well, that may or may not be true. Because sometimes 1.5, don't worry about it. Just, let's say it can't happen. So here's something else. How many of you know about filters? How many of you have ever used a filter for your water? How many of you have ever used a filter for your ears? How many of you have used earplugs? Nobody's used earplugs before? Yeah, that's why you're all going to go deaf. I should start yelling at you. How many of you have used earplugs? None of you. You should use a, thank you, Monica. You gotta protect your hearing, right? Yeah, because guess what? You only get it once. And I'm gonna tell you right now, you are going to be the first generation to lose your hearing before people older than you. And do you know why, Madison? Earbuds. You don't use earplugs, and you use earbuds. And we're going to talk about why earbuds are a bad idea. Over the ear, so that's why everybody should love Dr. Dre, right? Except then when he came out with the earbud version. The over the ear was so much better. If he had stuck with that, I wouldn't have a problem with him. But, you know, we kind of have this problem now about your hearing health, and always go over the ear. I know it's more expensive. I know it makes your head look really wide, but you'll be able to hear things when you're older. Like 35, you'll still be able to hear things. Otherwise, you probably won't. So hang in there. All right, this is that same sound wave, right? And we can do the Fourier transform on that, so we can plot our amplitude and our frequency. We just saw that. What's this dot represent?
Fundamental.
Yeah, the fundamental, right? It's the fundamental. Why? Highest amplitude, lowest frequency. Okay, not a big deal. Now, we can send this through a filter. Now, this filter can be mechanical. It can be something you create. It could also be something like your head. Your head can act as a filter, right? How many of you have ever been yelled at when you were in a different part of your house from the person who yelled at you? Has that ever happened, Marissa? Yeah, like somebody like your mom is like somewhere else and she's like, Marissa, and the walls act as filters, right? And they're going to filter out certain frequencies, okay? Because they're a physical barrier to these particular sine waves, these harmonics. Some harmonics will not travel through, right? They'll get filtered out. So if you look at this, we have a filter here. And then now we have a new sine wave, or a new set of sine waves. We lost a few sine waves, right? Do you know how we can figure out which sine waves we lost? You can do a Fourier transform after you filtered it. And look, we lost all of those high frequency components. That's pretty awesome, right? This type of filter, we would call this a low-pass filter. Why would we call it a low-pass filter? It passes through the lower frequencies, right? Okay. If it's a high-pass filter, guess what gets through? The higher frequencies, right? There's one other kind of filter. It's called a band pass, right? This is if you're in the band, Marissa, they'll let you pass. No. If you are within a certain range, right? It may not be the highest, it may not be the lowest, but you're somewhere in the middle, right? And that particular band of frequencies can pass through. That's a band pass filter. So you can chop off the high frequency and the low frequency and let a chunk in the middle go through. So that's pretty cool, right? So that's how filters work. We'll talk about filters some as we need to. Typically, we're going to assume this is linear, so it's going to have the same effect on every frequency or group of frequencies, right? So, any sound transmitting medium can be viewed as a filter. So the door to your bedroom can be viewed as a filter, right? Sound will come through there. It's really important to keep in mind that sound comes in, but sound also goes out, right? So that can modify the behavior while you're in your bedroom, right? So it's an important lesson you might have need to know a few years ago, but you're getting it now. That sound does go out if it goes. Filters work in both directions. Word to the wise there. If we know how that filter attenuates, alters, changes simple sine waves, we can predict its effect on any complex sound, right? Because we can, again, pull out all those sine waves and we can do that analysis, right? Also, filters will not add components. So they won't add sine waves, they'll just take sine waves out, okay? Or they'll decrease their amplitude. And sometimes they'll decrease their amplitude to the point that they disappear. This is sort of cool. This is that same clarinet, right? here at the top. At the bottom is going to be human speech, so we can think about that. But this is nice here at the top. The axis here at the bottom is going to tell you over time. It's about 600 milliseconds. It's about how long. It's a little over half of a second. Here we have frequency between 0 and 8 hertz. That's kilohertz. So that's between 0 and 8,000 hertz. Okay? If you look at this, the darker the region, the higher the amplitude. So that's how this is represented in this graph, right? So instead of all of those kind of things that we were doing before, a darker region represents a higher amplitude. What does this sort of band of dark represent down here at the bottom? That's the darkest bar, which would indicate that it is the highest amplitude. It's also the lowest frequency, both of which would indicate that it is the fundamental frequency, right? Okay, I know, right? Like, but I still feel like there are 4 of you who don't get it. And so until all of you get it, I'm going to just keep going with it. If you look at these steps, right? So each time we're going up, these are even steps. They're whole number multiples, right? Okay. This is about, I don't know, that's about 0.75. Here's about 1.5, right? I don't know, right? I'm just making guesses. So you can keep going up. What's cool about this is it shows you that natural sounds are not necessarily constant in every frequency spectra, right? So if you look at this band, we're going to call this like 5.8 kilohertz, right? I don't know. So we're going to say, look what happens to it about, I don't know, 400 milliseconds in. It just drops off, right? It sort of disappears. But that fundamental frequency, that stayed strong throughout the entire note, right? So that's kind of cool. So you can really take these spectrograms and analyze a particular sound, and that can tell you a lot about what's going on. All right. That's sort of the end of the physics of sound. So I feel like you have some handle on sound. We're going to talk, this is going to be important when we come back in the next chapter when we talk about perception of sound, because we're going to revisit some of the ideas about fundamentals, about missing fundamentals, about harmonics, and a few other things, okay? What I'd like to do now is shift gears just a little bit, and so we can talk about biological aspects. And we can talk about different parts of your ear. You sort of have 3 parts. You have the outer, the middle, and the inner ear. And we'll cover all of that. The outer ear, right? This is that thing that you use to hold your glasses to your face. That's not your nose. You use your nose for part of that as well, right? But you have 2 ears typically. That outer ear is called the pinna. That's kind of that flappy thing. It's pretty flexible. Everybody, don't do it to you, but do it to your neighbor. Reach over and just like squeeze their ear like this, as hard as you can. I'll give you guys, this is a lab activity. It's going to be graded. No, just kidding. So there you go. So you have the pinna, that's the outer flap. The point of the pinna, the whole object of this, is so you can have earrings. No, that's not true at all. The point is for it to funnel and focus the sound wave into the hole in the side, because there's a hole there, right? Okay, sound has to get in that hole so it can go into the rest of your sort of sensory apparatus, right? The whole point of the pinna is to focus sound into that entrance and into the ear canal. And that meatus is just a hole. Everybody's ears are shaped slightly differently. And if you were to cut your ear off, that would, 1, hurt. And 2, that would change your hearing, right? It would change the way that you hear. Okay? You can even do this with just like squeezing your ear, right, like gently, right? Because it can hurt if you do it too much. So you can like change the shape of your pinna just a little bit, right? And see how that affects the perception of sounds. It's kind of cool. The human ear, we're talking about human ears, are really effective at amplifying medium sound frequencies between about 15 107,000 hertz. Okay? That's not a high-pitched squeal. That's not a low-frequency hum. Guess what sound that you hear quite often typically falls in the range of 1,500 to 7,000 hertz. Like if you were going to classify sounds into large groups, what do you think one of the number one groups of sound would be? One of the most important sounds that you hear every single day, Abby. And I'm going to keep saying this until you sort of get it. Speech. Human speech is in this range, right? How many of you think human speech is an important group of sounds? Yeah, right? Because you need to know, like, I don't know, all kinds of things. So we communicate through human speech. Our pinna is designed, it evolved in this way, to specifically amplify those sound frequencies that are typically found in human speech. Now there are a lot of other sounds in that frequency range as well. Right? It's not just human speech. There are a lot of other things. But human speech happens to be really important one there. And we're going to explore this later, especially in the lab activity. But the filtering effect actually depends on the elevation of the sound source, which actually gives you some idea about localizing the sound, right? How many of you have ever thought you heard something? Yeah, right? And then Macy, you did this. You tilted your head, right? Anybody ever done that one? That is to change the orientation of your pinna in relation to the sound source, which is going to change the way that the sound is attenuated, right? And that can give you information based on how you've rotated your head and how the sound changes. You can get some idea about its location, right? In particular, its elevation. So that's pretty cool. From now on, when you hear something, try not to move your head and see how difficult it is to localize the sound. Alternatively, you could constantly just walk like this and then see if you get disoriented. That may be because of your vestibular system doing some funky things, but you're also not going to know where sound's coming from. Questions about that? How many of you want to switch ears with someone and see if it sounds different? It will. You know, you can. How many of you use earplugs? I'm just testing your memory because I already asked that, and none of you said. There are some of you who are like swimmers. Anybody a swimmer? Anybody ever been in water? Okay, yeah, there we go. Right. Thanks, David. I really like, yeah, I've been in some water before. Sometimes you'll use the like wax earplugs for swimming, right? Anybody ever use those? Take some of those wax earplugs and like don't stick it in your meatus, but stick it around in your pinna, right? To kind of like change the shape of it. And what you'll realize is that it actually sounds, the same thing will sound different. It's actually kind of cool. It's actually pretty profound. So, ear transplants. Possible, wouldn't recommend it. I think you can use super glue, right? Well, nobody's going to let me try that. Hey, so if we had the outer ear, we've also got the middle ear. Inside your middle ear, you have your auditory ossicles. These are the small bones, right? The incus, the malleus, incus, and stapes, right? The job of these bones is to transmit that sound energy that's coming in, right, to your ear and jamming around on your eardrum, also known as the tympanic membrane. It needs to transmit that sound into the cochlea, right? Now your inner ear, we're talking about the inner ear quite a bit, contains some fluid. You remember that endolymph that we talked about in the vestibular system? Okay. Your ear has that in the cochlea. You have that in your inner ear. If sound waves were to come in and we did not have this sort of transfer process, If they were to come in and they were to hit that fluid, they would bounce right off. How many of you have ever skipped a rock across a pond? It's the same concept, right? How many of you have ever jumped into a pond and it hurt, right? You hit the surface of the water. You're like, I'm going to do a face plant into this swimming pool, right? We've already established none of you are on the swim and dive team. So it's a possibility that you've tried this, right? So there you go. If we were just doing that into the fluid, then we would lose that sound and that energy wouldn't be transmitted effectively. With this tympanic membrane, with the auditory ossicles, we can transfer that energy without any loss, or with minimal loss, okay? And that's because we have different impedance levels. Not a big deal. Inside, so this is your inner ear. We've got your cochlea, right? It's a small coil tube that's filled with fluid. You've got the oval window at one side. Don't worry about this too much. Cochlea is divided into two parts. You've got a basilar membrane. We'll talk a little bit about that in a moment. When the sound wave comes in and it hits that fluid, right? So it's going to go tympanic membrane, auditory ossicles, then we're going to jam around on that fluid. We're going to displace that fluid, and we're going to move that fluid because that frequency, all those frequencies are coming in, right, Ty? So they're going to come in, certain frequency, and they're going to displace that fluid, okay? Somewhere along the cochlea. So here's your cochlea kind of unrolled. Not a big deal. So this is a really simplified cross-section uncoiled cochlea. This is the direction of fluid displacement. Okay? Not a big deal. All right. What's really important to keep in mind here about the cochlea is that near the base of the cochlea, it is very narrow and it's very stiff. And near the apex, it's going to be wide and flexible. Okay? That means it's going to selectively vibrate at a different frequency, or be able to be vibrated at a different frequency at different points along the length of that cochlea, right? So, a frequency of 500 hertz is going to match sort of the natural resonance of a certain location on the cochlea. If it's 1,000 hertz, it's going to be a different location. If it's 1,500, 20,000 hertz, whatever it is, it's going to be at a different location along the cochlea, right? The higher frequencies are going to be represented near the base because that's going to be the stiffer part, right? So it's going to vibrate at a higher frequency naturally. And then the wide flexible part near the apex is going to be for lower frequencies, okay? So when a low frequency comes in, that part of the cochlea near the apex is going to be moving the most, or the fluid there is going to be moving the most. If it's a higher frequency, it's going to be closer to the base. Okay. This fluid displacement is going to take the form of a wave. Again, we've got a wave coming in, not a particular surprise. And where that peak is, where we have the peak sort of that wave, is going to be a particular location on that membrane. Right. This is a 200 hertz tone, and we are measuring distance from the stapes, right? So what you see is the peak is somewhere around right here, right? The peak of that displacement. That is the part of the cochlea that is most sensitive to this 200 hertz frequency. If we increase the frequency or decrease the frequency, this peak will shift in one direction or the other. Okay? Higher frequencies are going to be closer to the stapes, right? Because that's going to be that stiff, narrow part. Lower frequencies are going to be farther away. It's going to be the wide, flexible part. This is one reason. If you lose your hearing, which will happen, again, earbuds, because you're bypassing the pinna, right? You have a pinna for a reason. It's to help filter sound, not to bypass it, right? When you bypass the pinna with your earbuds, I think that's a bad idea. I've been telling people this for years. And then like a year ago, there was an article that came out that said, and it was all in bold, so you knew they were yelling, so that you could hear it. Because again, you're losing your hearing. That younger people are going to lose their hearing at a younger age because of that loud rock and roll you guys live. No, because of earbuds. Actually, because of earbuds. So how many of you use earbuds multiple times a day for hours on end? How many of you are going to go home and buy some over-the-ear earbuds? Abby's so mad she's like throwing her earbuds away as we speak. Down with Apple. Yeah, no, seriously, Apple's evil.
They're gonna take over the world.
And the ghost of Steve Jobs is trying to choke you with every last cent you'll ever make. You guys gotta watch. I mean, not that like, I mean, everybody's like, oh, Steve Jobs is so awesome. But then there's this like, his big rival was like Bill Gates, and Bill Gates is like, you know, polio not a thing anymore because of me. You know, and everybody's like, oh, Bill Gates is awful. But I don't know, Steve Jobs didn't really do anything nice to anybody, right? I mean, why is that? It's all perception, right? You put it in a fun package with a fruit on it, and you thought he was a nice guy. Right? I'm going to start wearing shirts with like fruit on it so people think I'm nice. Work for Steve Jobs. Right, Carrie? You're an Apple fan? Great. I like you better. I was a little on the fence about you until just then. All right, questions about this? Okay, awesome. Hey, oh, I think this is going to make noise. Hold on. No, maybe it doesn't make noise. There's no noise coming out. There was noise. So I know it works. Okay, no, there's not noise on this one. There will be noise later. All right, so here is the distance from the stapes again. Look at that. That's 200 hertz. So our peak for 200 hertz is sort of right here. Our peak for 1600 hertz, look at how far it shifts over, right? Closer to the base, because that's the stiffer part that's going to vibrate at that higher frequency, right? This is where we're getting that peak displacement of endolymph, based on the natural properties of the cochlea matching the frequency of the incoming sound wave. That's it, right? You guys ever seen that, what was it when that bridge collapsed? You guys seen that video, right? Where the resonant frequency of the bridge was matching the frequency of the wind, right? And it all started just, and the bridge collapsed. How many of you get car sick? A couple people, right? All of you would, if people had not, so when they first designed cars, they didn't do a great job designing the resonant frequency of the suspension to the resonant frequency of your GI tract. And those two things didn't match very well. And when they didn't match very well, your insides went, and then you vomited. And then somebody was like, struts. And they were like, okay, smooth ride. And then there was somebody in West Virginia who said, on struts, I'm going to put potholes everywhere. And so there you go. I don't know. Why doesn't West Virginia have a strut manufacturing company like Shocks and Struts? Because I think you would make a fortune here, because that's like the first thing to go out on your, right? See,
I just had mine replaced.
I know, right? And it cost you probably a kidney, right? Give or take, right? Give or take an adrenal cortex. Depends on if you got the nice struts or the not nice struts, right? They're expensive. But if we were making these in West Virginia, we'd be making a fortune, because everybody has to buy a pair every 3 weeks. Why don't you guys think of these things? What are you going to do with your life? Not start a strut and shock company, but you should. This is called frequency to plate, not the shocks and struts. The idea that there is a certain part of the cochlea that has a resonant frequency that is going to match a particular incoming frequency of a sound wave is called frequency to place conversion. That's awesome. Do you know why that's awesome? If a certain place, this place, the cells that are there, if they get excited, guess what we know? That is a 1600 hertz tone. If the cells that are over here get excited, that's in a different place, we know that is a 200 hertz tone. They're in two different places, two different frequencies. That's why it is frequency to place, right? The frequency is going to determine the place where those cells get excited. This is sort of, we're thinking like on sort of receptive field terms, right? Remember when you were stabbing people in the arm, and when you stabbed them in the arm, like in one location, well, they felt it there, right? So there's like a place. We're going to do this out in the cochlea. Because of these variations, we get that maximum displacement in different places, right? So we have the high frequencies near the base, the low frequencies near the apex. How many of you have ever had something, that's going to be a funky question. Let me ask it in a different way. What's another word for kind of like narrow and stiff? Is like, you think about something that's brittle, right? Okay. How many of you have ever had something that was brittle? Like peanut brittle. Anybody had that? Yeah, it breaks, right? And then how many of you have had Laffy Taffy? That doesn't break, right? It's really chewy. So we're thinking about the peanut brittle being the base and the Laffy Taffy being the apex, right? And if you were to drop those on the ground in their packages, because we're going to still need them, which one would break and which one wouldn't? Well, the Laffy Taffy never breaks, but the peanut brittle broke. The first frequencies that you lose, assuming that you are not in some sort of environmental situation where you're going to lose a different frequency first, like you're a jackhammer operator, you lose jackhammer frequencies. The first age-related frequencies that you lose are the high frequencies. Those are the ones that kick out on you first. Okay? And the reason for that is that's the brittle part of your apex, of your cochlea near the base, and so they're going to be more susceptible to damage. This is why sometimes people will, maybe you tried this, like you had like a really old social studies teacher in high school, right? And everybody turned their phone notification to that really high pitch, like beep, right? And she couldn't hear it because she was old and lost high frequency hearing. But all the students could hear it, and you're all like sending messages about how old and like deaf your teacher is, right? She had no idea what was going on. She was up there telling you about Mesopotamia or something. That's why you guys don't know anything. Right? I know this. Also, sometimes, like I know for a security purpose, like Walmart will do this. So if you go to Walmart late at night, there are certain departments where they will play high-frequency noises to try to keep kids out of those areas. Right? And so you're like going in there and you're like, for whatever reason, I need electrical tape at 3 in the morning, don't ask. And so you're like walking around trying to find electrical tape, and you go to the wrong department, it's like, meh. It's like, that's just a really annoying noise. If you can't hear that, go get your hearing checked. Or you could do what? Stop using earbuds. See, earbuds did not exist until I was an adult. So my hearing's fine. You guys, on the other hand, you're going to go to graduate school and people are going to have to yell at you because you're going to lose hearing. That's how bad it's going to be. I'm trying to really frighten you. I own stock in over-the-ear headphones, so I'm really trying to get you guys to buy some. That's not true. Oh, this is awesome. Inner hair cells. These are the guys that are actually doing sensory transduction. These are the guys taking the wave, because now we've been talking about sound waves, and then really now we're talking about like kind of water waves, right? Because it's in a fluid, we're still talking about a wave. But we have to take that wave and convert it to an electrical signal so we can send it to our brain. About 3,500 of these. When that fluid displacement occurs, it's going to deflect what we call the stereocilia. Okay? So kind of these like hairs sticking up, and when it deflects them, that's going to rip open ion channels, positively charged ions will come in, don't worry about that too much, and you will get cells that are excited, and you'll go, wow, I am hearing 3,500 hertz noise. That is so thrilling. I'm just glad I can do that. There are also what we call outer hair cells. There are about 12,000 of these guys. Okay. They don't do the sensory transduction. They're more for sort of gain control. And gain control is this super awesome concept, right? And we're going to talk about it when we talk about vision. We'll talk about it now in the auditory system. I want to give you some idea about this, right? So quite often, human sensory capabilities are really broad, right? So if you think about it, you have a really broad range. The problem is, not every cell or every group of cells covers that entire range, right? They may only cover a very narrow band. We have to shift that band, right? So let's imagine you can hear any frequencies in a 500 hertz range. Okay? Now we know that humans can hear more than like 1,500 to 2,000 hertz, right? So how would we go about doing that? You can shift where that 500 hertz is, right? Where your attention is at any given moment on that. And these outer hair cells are responsible for that. Okay? How many of you have like a television? Yeah. How many of you have like a streaming service? You have access to Netflix or Hulu or whatever else exists out there in the world. Okay, so let's say you have Netflix, right? How many movies are on Netflix? 10,000. I don't know. I'm not making it up, right? Let's say you have access to 10,000 movies. That's awesome. Can you watch them all at once? You've got to decide which one you're going to watch, right? And I'm going to be honest with you, you're going to make the wrong choice a couple times. Trust me. They put a lot of bad movies on there. Right? And it makes me wonder, like, every month, why am I paying like $11.99 for this? So you can only watch kind of like one narrow band of content at a time, and you've got to adjust where that band is, right? And it's kind of that way with your auditory system. You can only hear a certain band of frequencies at any given time, and based on the environment, you're going to predict which band of frequencies you need, and then if something moves out of that, then you have to quickly sort of like flip your tuning to another sort of frequency band. It's actually pretty cool. Frequency to place code, we talked about this, not a big deal. Okay, let's keep moving. Here we're talking about that. This is also sort of related to gain control, coding intensity. We can actually hear about 100 decibels range, right? So that's kind of our dynamic range of hearing is 100 decibels. Okay. Each auditory nerve, though, can only hear about 20 to 50 decibel range. Okay? But each one is going to be tuned to a different set of these sound intensities, right? So one is going to be tuned to lower sound intensities, and another is going to be to higher sound intensities. So that way we can cover that whole spectrum, right? Just want to see how many slides we had left so we can make sure we get through this. Auditory nerves are going to come up and they're going to go to what we call the cochlear nucleus. This is once we've actually left the cochlea. From there, there's a very complex sequence of serial and parallel processing until we get to the primary auditory cortex. Here is a diagram of this. Okay. This is your left cochlea. This is your right cochlea. We're going to feed into your cochlear nucleus on either side of your brain. Then some of that's going to go up to an area we call the superior olive. These are a little more expensive than inferior olives, but it's worth the money. So you go to the superior olive. There is an inferior olive as well. The superior olive, in all actuality, is above the inferior olive, that's superior, inferior. Right, that's what that refers to. Not only does it send information to the superior olive on its own side, it actually sends information across. And on top of that, we're also going to send information to the opposite inferior colliculus, and then the information that we get into that superior olive is going to go to the inferior colliculus on our own side, and then we're going to go up to the medial geniculate, which is in the thalamus, and then on up to primary auditory cortex. I'm not going to expect you to memorize this path. It's kind of confusing. But we should think about it for a moment, because what's really awesome, and we're going to spend some time on this later, is knowing where sounds are coming from, right? How many of you think that it is important to know from which direction a sound is originating? If you don't believe me, the next time you're out in the middle of 20th Street, right, Imani? You hear a sound, just take a random guess which side it's coming from. Oh, that car may be coming from the left and it may be coming from the right. Don't bother trying to figure it out. Go like, I hear a sound, is it randomly gonna jump a certain direction and see what happens? My assumption is that's not the best way to do things. That's just a guess on my end. I mean, you guys try whatever you want. We've already collected your tuition for the semester. Right? You guys have already paid your bill. If you've not, play it safe for a few more weeks until you do. Okay, Abby? But once you've paid your bill, live wild and free. It doesn't really matter to me. Especially if you're graduating. How many of you are graduating this semester? Yeah, I really don't care what you do. Because I don't even have the opportunity to get money from you again, unless you're coming here for graduate school. But if you're not, somebody else is going to try to make a buck off of you. You want to buy a set of shocks before you leave? But it's going to do that. All right. So Natalie, this is confusing, right? But why do we do this? It's really important to compare time differences. Okay. How many of you have a head? Here's how you can check, and you'll know if you have one. Right? If your hands don't hit, there's something there. Now, put your hands up like this, and then that's how wide your head is. Just that's where it looks reasonable. So your head has some width, right? If there is a sound to the left of you or to the right of you, it's going to hit one ear slightly before the other ear, right? If for no other reason than your head is this wide, right? I think the average head width is like 9 inches. Does that seem reasonable? Somebody can look that up. Like I think the average distance from ear to ear is like maybe 9 inches, 7 to 9 inches. For some reason, I feel like that's a right answer. Could be wrong. So that's some distance, and because we're not traveling instantaneously, we're traveling fast, 335 meters per second, right? So Chuck Yeager's just zipping by you. But there's some time delay there, and if we can compare that time delay from the left ear to the right ear, guess what we might know? We might know exactly how far over it is from you, left, right. If it's all the way over, then it's going to be maximum time delay. If it's not all the way over, right, if it's just a little bit from the midpoint, then that time delay is going to be smaller, and we'll know where that sound is coming from. And that seems beneficial. Who remembers that time I talked about like what and where, like dorsal and ventral processing? Okay, we're going to have that going on here with the auditory system as well. Not too much to think about here. When we do sound location, they're what we call binaural cells. They're getting information from tube. They're going to be out there in that superior olive. We have what are called ITD. That's interaural time differences. Okay, that's going to be, when does it arrive to one ear, when does it arrive to the other ear, and we can compare that. Okay. Interaural level differences are going to be related to amplitude. Okay, because your head is a filter, it can cause amplitude to go down. Also, when I talk to Carrie, who is sitting as close to me as possible for a student, the volume, the sound amplitude that she's getting is maximum. by the time it moves to the back of the room and probably to the other room and goes through that wall, because I'm imagining they can sometimes hear me, that amplitude has decreased over time, right? How many of you live near a train? How many of you have ever seen, yeah, Macy, so I've never managed to live very far from railroad tracks, which I don't know if that says much about like my ability to earn money to live in a, right, like I always live next to railroad tracks. But I've also sort of always lived in areas that have been like really reliant, or at least at one time, upon the rail industry, right? So that train, when it's really far away from you, it's kind of like not very loud, right? But when it's right next to you, it's really loud, right? And that's because over distance, amplitude decreases, right? And we can measure that if we want, we're not gonna worry about it. So we can measure interval level differences, again, because your ears are some distance apart, right? Somewhere between 0 and 8,000 inches apart, right, Marissa? There's going to be an amplitude decrease from one ear to the other. Okay? If there's not an amplitude decrease, guess where it is? It's either directly in front of you or directly behind you, right? Because it's going to be the same amplitude in both ears. All right, auditory cortex, it's kind of out in the temporal lobe. You've got some association cortical areas around that. This is mapped what we call tonotopically. This is sort of interesting. Remember when we talked about the somatosensory system, and we said that was mapped like the body was sort of mapped somatotopically on there. This is going to be mapped tonotopically, such that, and here's your primary cortex, high frequencies, and then you're going to progress to low frequencies. Okay, and each of these bands sort of represents a shift in frequency from a high frequency to a slightly lower frequency. You're going to kind of step down. Now there's a reversal here. Don't worry too much about this, because as we're going from like primary auditory cortex to secondary auditory cortex, it's typically mirrored, right? This is sort of a general organizational principle of cortex, is that when you move from one area to another, and if it's still auditory cortex, it may be handling a different kind of information, but it's going to flip the map. It's just going to be a mirrored image. All right, descending fibers, cortex to cochlea, they're going to be in reverse order, don't worry about it. This is what's going to go back down, though, to those outer hair cells, right? So that we can sort of drive attention and those amplification functions, right? It's really important to kind of have this feedback loop going, right? So you can tune those cells to the specific frequencies that are present in your environment so you can extract the most information possible. Okay? And if there's an outlying frequency, you want to be able to shift to that pretty quickly, so you want to have some cells that are ready to gather that information as well. Does that work? All right. That was chapter 4. Now we need to do chapter 5. Which again is not really going to feel like much of a shift, because we're just going to be taking those same principles we talked about in chapter 4 and sort of applying those to sound perception. Try this one more time. See, Justin, when I open this, and it comes up in protected view, which I understand, I should be able to click this OK button, and then I should be able to click Enable Editing, and it doesn't always let me do that, and I don't know why. All right, so perception of sound. We're still talking about the auditory system, right? So everybody's still excited. All right, don't worry about these learning objectives. Let's just hop into it. Loudness perception. This is important, right? How many of you have heard someone say your name? That's a reasonable thing, right? So they're going to say your name. They're going to say Joseph. And there's nobody in this class named Joseph as far as I know. At least as a first name that I can see on your roster. And if somebody says, hey, Joseph, you're going to respond to that in a story. Somebody says, hey, Joseph, and that's a completely different thing. So we need to understand how we're going to perceive sound, right? So how do we do this? Loudness is different than amplitude. They're connected, okay? But amplitude was that measurable quality of the sound wave itself, right? That's what we're talking about. Loudness, on the other hand, is going to be your perception of that, and it is related to physical intensity. Okay? There are some ways that we can do what we call loudness matching. So we'll take a comparison sound, and we'll adjust that until it matches a fixed standard sound. So there's going to be a sound of a certain intensity, and then you're going to have a knob on a speaker, and you can adjust that sound up and down until they match. That's pretty cool. What's really kind of interesting is that low frequency sounds lack loudness compared to high frequency sounds. And what we mean by this is, so a lower sound can have a higher intensity than a low frequency sound can have a higher intensity than a high frequency sound, but you will indicate that the high frequency sound is louder. Okay? How many of you love to hear screeching noises? This is not like let's find who the weirdo is in the class kind of question. Nobody likes screeching noises, right? That's a reason that they're called screeching noises. Nobody likes that. And so when you think about, like, what is a really annoying screeching noise that you might hear sometime? Like, who loves the sound of a crying baby? Nobody. Not even the baby. That's why it's doing it. So you'll make it stop. That's why babies cry. Don't have babies. Macy, that's a true story. Don't have babies. You'll save, think about the money you'll save. You'll live longer, right? Because you're not going to have this sort of drain on your life. Think about the drain you are on your parents' lives. Your parents are going to die probably 5 to 10 years younger than if they hadn't had you. I don't know if that's a real statistic, but that's what I think. I've probably shaved off 10 years of my parents' lives. So some of you are worse than I am, right, Abby? So who knows what you've done. So think about that. Like, if you want to live a really long time, don't have kids. I think that's a better way to do it. Right? So, screeching noises, you're going to think that's louder, even though it's not, you're going to perceive it as louder. And it actually makes some sense, right? How many of you, when you've been in pain, you've ever gone, ow? Nobody does that. Nobody has this, like, there's not a low-pitched squeal of pain, right? That's not the way it works, okay? When you are in pain, it's a threat, right? How many of you love the sound of fingernails on a chalkboard? Oh, that's like my favorite, right? Nobody likes that. There's actually some idea that maybe that's actually that frequency is really high, and it's really close to sort of alarm calls used by other primates, right? Like monkeys and apes. And so, evolutionarily speaking, that particular frequency should get you on edge, because when one of your buddies goes, that probably means they're in danger, right? And so they're going to have that high-pitched squeal. I worked hard on that, by the way. I really worked on that squeal like you wouldn't believe. So when they have that high-pitched squeal, that's a threat sign. You should get your attention. You should perceive that as louder, right? Because that's just the story, right? How many of you go into the woods for extended periods of time? You like hike. How many of you take a whistle? Yeah, you should always take a whistle, right? Their whistles are great for a couple reasons. One, they're going to be easier to hear than you going like moaning in pain, right, if a log falls on you, which happens. Two, they're easier to make a lot of noise. This is just a safety story. They're easier to like, because you just have to kind of like breathe to make a whistle work, right? And you don't have to put as much effort into that if you're injured or running low on like food and energy and things, right? A lot of backpacks have integrated whistles. So if you have a backpack, they'll be sort of like integrated into the chest clip. A good place to put it is the chest clip close to your mouth. You never want to put it like on the like rain fly on the back, because that's kind of hard to reach the whistle back there. Just Oliver, if you ever get a like backpack company, you're going to design backpacks. Whistle on the chest clip. Anybody have a backpack with a whistle? Everybody's checking, right? Let's see if you have a whistle. No? Just carry one anyway. In case you're ever out in the woods and somebody commits like a traveling violation, you gotta blow the whistle. It's basketball season, you know, there's a good basketball joke. You never know when those squirrels, they don't dribble when they carry those acorns. Just blow the whistle on them. Sometimes there are fouls too with squirrels. All right, so there you go. That's kind of cool. Why is this the case? Why is loudness perception? What are some theories? So here is sort of, I'm going to do a little Shakespearean aside here and tell you something, Zoe, that's going to help you understand this class, right? The great thing about the author of your book is that he doesn't buy into a particular theory. He doesn't go, this is the way it is because this theory guy said so, and we're going to make everything fit that. What he will do is, and this can be a little confusing, but it's better for you, he will present to you multiple theories and the evidence that supports that and the evidence that doesn't support that, right? So that's what we're going to talk about here. So when we talk about some of these theories, we're going to talk about multiple theories. It's not important always that you remember all of the details, but just remember that there may be different ways to try to describe these things based on the evidence, right? That is, in all honesty, one reason I really like this particular text. All right. So here's a basic idea. What we call the excitation pattern model, right? That proposes that loudness is proportional to total neural activity on the auditory nerve. Well, that makes some sense, right? If your auditory nerve is more excited, well, then that should mean that the stimulus was more intense. And if it was more intense, then that means it was louder. That's pretty straightforward, right? And there's evidence to support that. But there's evidence that says that's probably not what's going on. I don't know what happened there. And part of this is that human hearing has that dynamic range of 100, 120 decibels, but each fiber is only going to be in that, remember that, like 30 to 50 or 60 decibel range, right? So, if it's like, whoa, it's going to be at 120 decibels maximum, right? And actually it's going to be higher than that because we don't hear things at 0 decibels, right? There's going to be some threshold and then we're up from there. But let's say it's up at 150 decibels. Only half of your nerve fibers are excited by that, right? The other half are that low intensity, they're not even active. So no matter whether it's a high intensity or a low intensity, only about half of your nerve fibers are going to get excited at any given point anyway, right? So that idea of that excitation pattern doesn't really seem to matter. Okay, so that theory probably didn't really work. But who knows? All right. Now we're going to get into some stuff about pitch perception. This is if you can decide if it's a curveball or a slider. No, that was a baseball joke. It's almost spring training, so I got to throw a baseball joke in there, right? You can tell if it's no, I'm not going to tell you how you know if it's a curveball or a slider. Mostly it's based on velocity, right? That's the easiest indicator of different pitches, in case you want to know that. In case, Kerry, you're going to try to make a run for Major League Baseball this year. You scoffed at that, but no. All right. Pitch is the perceptual attribute that we correspond with frequency, right? Higher frequencies, higher pitch. Lower frequencies, lower pitch, right? That's not a big deal. We're actually pretty good at this. We're actually pretty good at pulling out frequencies. You can actually create what we call a masking noise. So if you think about some white noise, would be a good masking noise, right? You guys know about white noise, right? It's kind of just, that's white noise. They make these little machines. How many of you have like a sleep machine? Anybody have one of those?
I just listen to it on my phone.
You listen to it on your phone?
Yeah.
Then you have a sleep machine. All right, it's the same thing. But do you do the white noise, or do you do like waterfall, or ocean, or what else do they have? Like rainforest, and there's always like a toucan getting strangled. Right? You guys ever listen to those? Right? It's the truth. So, you can have that masking noise, the white noise, and then you have some signal in there, right? What is that other kind of frequency? And so you're going to have that playing, so that's going to be awesome. Masking is effective when the noise is similar to the signal, right? So when those two frequencies are close together, then it's kind of hard to pull out the signal, right? If they're not close together, then it's pretty easy. Okay? This is kind of cool because it matches actually what we see in individual nerve fibers. So this tuning capability matches what individual nerve fibers do, indicating that we have frequency-tuned nerve fibers. Okay? So we have specific nerve fibers that are for each specific frequency. And if that frequency is present in that signal, then that nerve fiber is going to get excited. If there are other frequencies, like in that masking noise, then other nerve fibers will get excited, and we'll be able to know that. If the frequency and the signal, or the mask and the signal frequencies are so close together, then really that same nerve fiber is going to get excited, and we're not going to know what's the mask and what's the frequency, right? This is pretty awesome. There are all kinds of like what we call frequency discrimination experiments. Okay? So we really want to see like how good are you at telling the difference in frequencies. Okay? We're actually very good at low frequencies, as much as a 1% differential threshold, right? We can go as much as a 1%, as low as a 1% difference in low frequencies. We can tell that that's different. When we get to higher frequencies, we sort of lose that ability. So higher frequencies, we're not as good at telling that they're different. Okay? And that might be because all high frequencies are just, screams of death. And it doesn't really matter. We should respond to all of those equally, right? Have you ever thought about that? This is a good mechanism, actually. Low frequency, like let's say normal frequency, you can tell who people are, right? And there's some people you like. I'm assuming there are some people you don't. And those people that you don't like, if you hear them talk, what do?
I cringe.
You cringe, you throw things at them, you leave. If they ask for something, like if you just heard, if you had your back turned and you heard someone say, "Hey, can you help me?" But you know it's someone's voice you don't like, what do? I didn't hear that. If it's somebody you know, Imani, you turn around and you offer a lending hand, right? But if you hear a scream, you go help. You don't know who it is. Because we're not very good at those higher frequencies to determine, like, oh, that's whoever, right? So we lose the ability to determine higher frequencies. So that's really a great trick that those people are playing on you that you don't like. Right, Marissa? Because they're not using their low frequency scream. They're using their high frequency scream, so you don't know who they are.
I have a question. I go to a lot of rock concerts, and I don't know if this is like actually this, but there was one that was inside of an arena,
Yeah.
and people were screaming very loudly.
Yeah.
And then when you actually listen to whoever was on stage, their voices sound distorted. Like they sounded like chipmunks. Why is that?
Wow, that's pretty awesome.
It was terrifying.
You don't like the Chipmunks? They made a great Christmas album. Does anybody have that? I hate Christmas music, even Chipmunks Christmas music, I'll be honest. Every year for Christmas I ask for January. It's like, please. So, that's actually a great question. And I'm not certain I know exactly what happened.
Like it's happened on several occasions, and everyone, like, not on outside concerts, but like inside of the venue.
Right. I'm thinking that there's some interference of sound waves that are sort of like intersecting with each other based on all the scream. Why do people scream? So this is something, right? Like if I want to scream, like I've got places I can do that, but I'm not going to pay like a lot of money to go scream while I'm trying to listen to somebody sing,
Like,
right?
I understand.
Aren't you paying to hear them sing?
Yeah, I get that you're really excited, but then like my ears like hurt, and there was like a buzzing noise like for
That's why
a
you're gonna
long
lose
while
your-
after the concert ended.
That's scary.
Yeah.
random note. I pulled up Fourier analysis of you two talking, and when you talk, you're in the range. The musical note is A, B, C.
Yeah.
Kind of, and when she was speaking, it's F sharp and G.
Wow, how about that? I don't know what that means for you in your life, but there you go. You can compare that to, I'm sure there's like a website where you can compare that to famous people. Like what range, how many of you talk in the same range as, Franklin Roosevelt or something, right? I don't know. Do you ever, we should start that website, Montana. I think that's a winning website. People would pay to figure out like which famous person you sound like based on recordings that we have. Hey, speaking of that, this is a sort of related story to your thing and Montana's thing, and also to the Hindenburg, because you never get enough Hindenburg stories. So, how many of you have heard the recording of the right? Oh, the humanity, right? So we've all kind of seen jokes of that, right? So the broadcast of that sounded really horrible, right? It's like this guy's like, oh, the humanity, right? Not at all what he sounded like at all. That guy was actually known for his like deep, smooth voice.
Wow.
I know, and so it's actually the recording. So I watched this documentary about it. I think it was from PBS, where they actually had other recordings of his radio program. He was a radio journalist, right? And so they actually slowed down his the recording and actually matched it to what it should have been, and it's a completely different experience.
Well, that like in one of the instances where this happened at a concert, my friend had taken a video,
Yeah.
and I was like, I wonder if it sounds like that, and it doesn't. Like if you like when you hear their voices, they sound normal, but to us, it was the worst thing I had ever heard in my life.
There you go.
And it like stopped halfway through the set, but
Yeah.
because people stopped yelling as much.
So now I think I'm going to start a rock band and have like a 20-minute scream session for the audience before I start playing, so that people can really commit to my art. Nobody thought that was funny. That's interesting. So the next time you go to a rock concert, you're going to have to take some recording equipment. Now not like, because they're going to get upset if you're like recording, like if you're in there with like professional recording equipment trying to rip them off, right?
You're not allowed to have this.
Yeah, but try to go in with like a Fourier analysis machine, and just tell them that's what it is, and tell them you'll like post it to the band's website.
In like the middle of a mosh pit.
Yeah, that would be something, right? And it's like you're out. I don't know, things I think about. Nobody's excited about that, right? All right. No, we got to get to moving because we got a lab to do. Pure tones, neural activity, pitch, frequency to place. We talked about that, and timing. Don't worry about this too much. Helmholtz. Helmholtz, man, that guy was a genius. He actually thought about like the basilar membrane vibrating in sympathy with the frequency of the incoming sound wave, and based on that, he came up with what he called. Basically he came up with the first idea of pitch perception, which is now place theory, which is really kind of how things work. There's some other idea that timing, there's this timing theory idea. So you have neural firings, right? Because you have all these nerve cells, like these neural cells in your auditory system, right? And they're going to be firing action potentials. And based on the gaps between those bursts of activity, you can maybe determine pure tones that way. Complex tones, on the other hand, are complex, right? So, no pun intended, it's really true. We've got, remember, those harmonics and the fundamental. What's the fundamental? Highest amplitude, lowest frequency, right? So that's going to be the fundamental. Right. Typically, when you listen to a complex tone, the pitch that you perceive is going to be that fundamental frequency. We talked about that, right? So whatever that fundamental frequency is. However, there's this really awesome thing called the missing fundamental, where you can remove the fundamental, right? We're going to do that Fourier analysis, find the fundamental, filter out the fundamental, leave the harmonics in place, okay? And when you do that, you're still going to hear a pitch that corresponds with the fundamental frequency. Obviously, Madison, this creates a major problem for people who think the fundamental is the frequency that's giving you pitch perception, right? If I can remove the fundamental and you still perceive the same pitch, then it's probably not the fundamental that's doing it, right? Although, as we'll talk in a few moments, it might still be related to the fundamental in some way, right? So, we've got our temporal theory, okay? This is when we talk about something being synchronized to the beat frequency. Beat frequencies are present in complex sounds, even if the fundamental component is absent. So who remembers that time I told you that harmonics are whole number multiples of the fundamental, right? So we're going to have components of the fundamental kind of embedded in that harmonic structure, right? And so that beat frequency is still going to be there. This temporal theory can actually explain how the missing fundamental works. Some folks call this a residue pitch, right? If you remove that fundamental frequency, you can still perceive that. We call that the residue pitch. There's also something called pattern theory. This was this guy Goldstein back in the 70s. Basically, the idea here is that you're trying to find a series of harmonically related frequencies, right, that fit the resolved components as closely as possible. Okay? So you kind of find this best fitting harmonic series, and of course that's going to be related to the fundamental, because again, harmonics are always whole number multiples of the fundamental. This can explain the missing fundamental effect, because the pitch of the fundamental is of course defined by the harmonics that are present, right? So if I give you harmonics that are 15, 20, 30, 70 hertz, you can use those numbers to find sort of the lowest common denominator, right? You guys have done that kind of math before. And you find that lowest common denominator, that will tell you what the fundamental should be in that series if we remove that fundamental, right? So that's pretty cool. There's also this idea, this autocorrelation theory. This one's kind of complicated, but basically you try to find these prominent interspike intervals, which is the pitch, by playing a delayed signal of the incoming signal, right? So you've got that incoming signal, you play a delayed signal, and you compare those two, right? And when you do this, you can find sort of these high correlations with the delay. This is kind of complicated, right? So I'm not going to ask you a whole lot about this autocorrelation, but you do need to know about it. Okay. Let's see. All right, we're doing okay, but we do need to move quickly so you guys have time for a lab activity, which is going to be super awesome. All right. Auditory localization, we've talked about this a little bit. Pay attention to this because your lab is going to involve auditory localization. Sound direction in what we call the horizontal plane, that's left to right, is specified by an azimuth angle relative to straight ahead. So if straight ahead is like 0, and then like this is going to be kind of like 90, 45, right? So you've got that. The up and down or vertical is going to be an angle of elevation, right? Okay. And this can be kind of think about from your ears, so it can be up or down, right? So kind of go up or down. And then of course that third dimension is going to be distance. And we can estimate distance as well. When it comes to the azimuth, this is your sort of left-right plane, right? We have what's called the minimum audible angle. This is the smallest change in azimuth angle that can be detected. Okay? Performance is going to vary with sound frequency, but it's going to be really bad between 1500 and 1800 hertz. We'll talk about why that is. Okay? When you are switching, or when you're moving right around 2000 hertz, right? We're just going to be right around this range. Below 2,000 hertz, we're going to use that interaural timing difference, that ITD, right? Okay. We're going to be using the difference in time of arrival from left ear to right ear or right ear to left ear to determine location below 2,000 hertz. Above 2,000 hertz, we're going to be using level differences. So we're going to be using amplitude differences above that. Okay. Obviously, at this switch point, we're not going to be doing well. That 1,500, 1,800 hertz is right in that range, right, Justin? Now, if you think about this for a moment, anything above 200 hertz, the higher the frequency, right, the closer your peaks are getting together, the harder it is going to be to determine which one arrives first, right? Because the peaks are going to be closer together. It's going to be more difficult. But lower frequencies, it's going to be easier to do. Elevation, remember that filtering with the pinna, okay? So we can kind of move our head around and we can get an estimation of elevation. Distance, again, is going to be, a lot of that is going to be with intensity. So here's kind of the mathematical formula. Decreases by a factor of 4 for each time you double the distance, right? So it drops down quite a bit for every time you double distance. Not a big deal. Oh, precedence is kind of interesting, right? We got to think about echoes. How many of you love echoes? I should go echoes, echoes, echoes. I thought that was interesting. So there's an effect called precedence. Your auditory system is only going to pick up on the earliest sound coming, and that second sound is going to be sort of perceived as an echo, right? If for some reason you didn't perceive that as an echo, it would be difficult for you to determine where the sound was coming from, right? You can see where an echo would throw you off on that. All right, I'm going to click a button. This may be painful. It wasn't painful. I wanted to... Okay. Let's see if this is painful. That's not so bad, right? Okay, this is precedence. If we play both of these at the same time, that's clearly just a series of one tap, right? And there are several of these. There are 5, but they're 5 single taps. We don't have an echo, right? Okay. Now, depending on where you're sitting, because I'm not sure how these speakers are wired, which is going to make a difference to your sort of stereo environment. So we have sort of 4 speakers. I'm going to play with a 5 millisecond delay, and let's see how this sounds. Now that sounded different, right? It sounded like it was a little sloppy, right? Okay, you wouldn't describe it as 2 separate sounds, but it wasn't this same crisp single sound, right? And here we can play the other side of that too. Okay, so there's a little delay. Now if we had to play the longer delays, it's going to be 50 milliseconds. That's clearly 2 sounds, right? So now they've separated out into 2 sounds instead of that sort of echo. So there you go. There's how echoes work. And your brain's smart enough to know if the 2 sounds come close enough together, it's the same. And so we're going to say it's coming from the same place. If they are 2 sounds, then there we go. Let's not worry about formant frequencies. We're not going to talk a whole lot about speech. Speech has sort of its own brain circuits. Not a big deal there. Spoken word recognition obviously is important, but again, we're going to skip over that. Auditory scene analysis, we'll talk briefly about this. You've got an environment with an incoming sound wave. It's got to be partitioned into different sources, right? And there are different ways that you may go about doing this. this. You may decide music, voices, traffic, those go in different ways. And you have auditory streams to do this. Some of this is going to be related to temporal proximity. I like how close are two sounds together, how similar are they, location, right? I don't think most of you were confused when I played the sounds through the speaker as to whether or not that was me or my voice is me, right? Because the sounds are different, the location was different, right? So you're able to do that. These are kind of cool. This may be painful. It plays for a lot longer time than I thought it did. I forgot. So there you go, right? So that's sort of, you can kind of hear that. Well, let's go play this one. I think it's obvious that third series, those are two different streams, right? You kind of have the high pitch, beep, beep, and then the low pitch, bump, bump. And they're two separate streams, right? And that's because of the difference in pitch, the difference in frequency there, and the timing difference, right? When we put them... That's kind of cool. And then you can play this one. I like this one. I'm going to play this one more. So much fun. Hearing dysfunction. We're not going to talk a lot about this. There are a lot of reasons why you can lose your hearing. You can have damage to the tympanic membrane or your ossicles. You can have nerve damage there to the auditory nerve, or you can have damage to your your brain, like central processing. There's a bunch of stuff there. We're not going to worry about that. Hearing dysfunction. All right. Now, we need to do a couple things. There is, so we're going to have a lab activity. So that's awesome. We've got like 27 minutes. It's going to be cool. There is also there's going to be another sort of lab that I want you to do. So there's going to be kind of like two parts of the lab. Do I not have that posted?